A very good evening to all of you guys. My name is Rahul KANYAL, and we are going to proceed with our prior discussion that we are done. And here also we are going to talk about casting process part 2 here. All right. Now how are you doing, guys? Now, if you have not subscribed to our channel, please do it right now. All right. Keep on sharing these videos and keep on liking these videos, guys. Okay. Yep. Now, okay, so this is my profile. I'm a senior faculty for mechanical, GATE and ESE, and I take concepts on fingertips production classes daily at 2 p.m. guys. All right, now this is our target GATE 2021 course, and you can always start a free trial with us. All right, yep. So so let me get started with this. So how are you doing, guys? So start free trial, that's what we say, right? So the trial is absolutely free for you. Okay, and yep, so I'm just trying to get hold of okay, now let's jump to the straightly to the questions. And today also we'll be doing something similar to what we did yesterday. All right, so we are going to understand or improve our understanding through questions. All right, now yes, now light impurities are prevented from reaching the mold cavity by providing. All right, now this is a diagram, and you can see here we have put strainers. This portion over here is called a strainer, right? And this portion over here is splash core, and this is skim bob over here. Okay, so what do you think about this? Light impurities are prevented from reaching the mold cavity by providing. So which answer will you say, right? Just type in your answers, guys. Okay, and yep. So please just think about this. This is given to you, okay, and the diagram is given to you. So what do you think about is is the question here, right? Until then, I'm going to just figure my the system, right, the feedback system, because I'm not getting the feedback here. Some problem with the feedback. So till then, just talk about this, guys. All right. Okay, I'm not getting any. Okay, so what do you think about this question? Okay. Yes, so I got it. Now I've gotten it. So yes, so C, people are saying, Shripad also says C, and Sanjeev also says C, Sanjeev again C. Hey Lokesh, I'm really good. All right, thank you very much. So Ningana also says C. So what do you think about this? All right, so it says that, okay, strainer here. Okay, so let me tell you that strainer is used for, just solid impurities. Okay, the word that we use for strainer is solid impurities. Okay, it takes away solid impurities. Splash core, what it does is it prevents the molten metal, okay, to fall directly on the mold. All right, otherwise it damages it. So that's why we use splash core. Okay, and obviously it's written over here, right? The skim bob here. Okay, the lighter impurities actually they float on the top of skim bob, and heavier impurities they go down. Are you getting this? So the answer has to be skim bob here. Are you getting this, guys? Hello? Yep. Is it good? Yes, so answer is skim bob. So yeah, Samarth, you're right. All right. So good, guys. So could you understand this? So the difference between strainer and skim bob, strainer just takes care of solid impurities here. Okay. We call it dross actually, D-R-O-S-S, dross. But no need to remember this name even, but just think about the solid impurities. Okay. ठीक है? Okay, Logesh, you are from BHEL Township, Ranipet. Do you know me? Okay, I was also there, right? Yes, so yes, let's get started with this. Which of the following materials requires the largest shrinkage allowance while making a pattern for casting? Okay, so we just have to talk about largest shrinkage allowance. Okay. Is that good? Yep, and I request you again once more to share this video with others, and they might also be benefited using this video, guys. All right, so largest shrinkage allowance. Okay, now shrinkage allowance, let's talk about this. So what do you think, guys? Okay, so shrinkage allowance here, okay, is directly proportional to, let me tell you that this directly proportional to coefficient of thermal expansion. All right, coefficient of thermal expansion. Always remember this. Okay, yes, TPM, you're right. Long time no see. Okay, so shrinkage allowance is directly proportional to coefficient of thermal expansion here, right? So which one of these has highest coefficient of thermal expansion that you need to know? All right, are you getting this? Hello, that's the hint for you. That's the hint for you, right? So which one? Logesh says it's A. Okay, Shripat says it's A. All right, Sanjeev Kumar says it's okay. So 17 millimeter per meter. What is that, Sanjeev? Yes, TPM, I think. Yes, you're right. So which one has the highest coefficient of thermal expansion? So actually the answer here is A. All right, it has the highest coefficient of thermal expansion. All right, is it good? Hello, is it good? So just remember this, guys. All right, that aluminum amongst these has the highest coefficient of thermal expansion. All right, so that's why the answer here is aluminum alloy. Yeah, Sanjeev, you're right. Sanjeev, you're right. Bhargavi, you are also right. Right. Okay, now the next question, guys. Okay, yes, you're right, Sanjeev. Disposable patterns are made of. Now disposable means, what is the meaning of disposable? Disposable, you can always think it's something like use and throw, right? You can always think of disposable as use and throw here, isn't it? Now, which one of these would you throw after one use? I'm going to repeat it. Okay, so which one of these would you throw after one use? That's what it is. Chalo. So yes, obviously, you know, this is wood, this is rubber, this is metal, and this one is a plastic. Let me tell you that polystyrene, this is a plastic, right? So which would you use just for once? That is what it's trying to tell you, right? Isn't it? Yes. So obviously the answer is this one, plastic. Plastic won't last, right? Isn't it? So maximum once we'll be able to use this if made properly. So the answer here is D. Yes, you're right. TPM, right? Is that good? Hello, Avinash, Rohit. Yes. So we are talking about here D. Okay, polystyrene. Okay, nice, guys. Okay, so Venkat, yes, Abhinash, Srinivas, you're right. Now let's do this question. We had already done this question yesterday, guys, and today let's also do this. Okay, shrinkage allowance on pattern is provided to compensate for shrinkage when? What do you think about this? Come on, let's do this. Yes. Chalo. So shrinkage allowance, we talked about it, right? It just takes care of which shrinkage stays. There are 3 stages, right? Yesterday we talked about it. 3 stages. So which one of the 3 stages does the shrinkage allowance takes care of? The first one is stages of pouring temperature. 3 stages of shrinkage, right? This we have already or always talked about. So the first one is the shrinkage when there's the temperature change from pouring temperature to freezing temperature, right? To freezing temperature, isn't it? Yes. And the second one is a phase change. Phase change from liquid to solid. Yesterday also we talked about it, right? From liquid to solid, isn't it? The third one is nothing but freezing temperature to room temperature, right? Freezing temperature to room temperature. And we said that, okay, the shrinkage that you know, we say that shrinkage allowance is pertaining to the third one, right? So that's nothing but freezing temperature to room temperature. Shrinkage is taken care by shrinkage allowance. Sorry for that. Is it good? Yesterday also same thing, right? So Harshvardhan, you're right. Solid shrinkage, yes. TPM, you're also right. Sripat, Sanjeev, Harshvardhan, Lokesh, yes, you're right. All of you, yeah, good. Congratulations, all of you, good. Well done. Okay. Yes. Is it good? Yep. Is it good? Okay, now let's next question. In centrifugal casting, the lighter impurities are. Okay, now this is the question. In centrifugal casting, the lighter impurities are. All right. So firstly, let's see what centrifugal casting is. Then you'll be able to answer this. Okay. Okay, so it's just an introduction to centrifugal casting. Just an animation, guys, all right? Just a 2-minute animation that will enhance your understanding, okay? Yep, so what happens here is that, see, this molten metal is fed into a rotating chamber, okay? And it can also be vertical as well as horizontal like this. Now, when it's fed, okay, because of the centrifugal action, all right, then a hollow casting is made here. Because of the centrifugal action, the hollow casting is made here, and this is the direction of solidification. All right. So what happens here is that the lighter impurities are thrown to the inner surface of it. Are you getting this? So I'm going to just play it again to you. Okay, so what happens is that, okay, again I'm telling you, okay, when a force molten metal is thrown into it because of the centrifugal action, all right, the metal flows along the rollers like this, and this is the direction of solidification. Okay, it always starts from the external diameter towards the inner diameter. Now what happens is these light impurities, okay, these light impurities are accumulated at the inner surface. All right, are you getting this? Because centrifugal force is nothing but mr omega square, right? Now more is the value of mass isn't it? The more is the value of mass, the more is the force here, right? The force is directly proportional to mass. So if mass is less, so force is also less, right? If mass is less, force is also less. So lighter impurities, they just stick to the inner surface of the casting. Now I have told you everything, right? So what do you think about the option here? So yes, so what do you think about this? TPM, centrifugal force, mass. Yes, you're right, you got it. Brilliant, right? So yes, so which one? Harshvardhan, Abhinash, Shripad. So what do you think about this? Sanjeev, D, is it D? Yes, it is D, all right. It will be collected at the inner surface of the casting, all right. Is it good, guys? Hello, is that good? It will be always collected at the inner surface of the casting, right? I have shown you why, because it's directly proportional to mass, right? Isn't it? So the force is going to be less if mass is going to be less as well. So lighter impurities are going to be at the inner surface of the casting. Yes, yes, Ranvin, you're right. Shripad, you're also right. Okay, yes, good, well done, guys. Now comes the next question. The primary purpose of sprue in casting mold is to. Now we have talked, right? This one is sprue here. This hole is sprue here, right? Okay, TPM, yes, no doubt. So what does a sprue do? So the question here is that the primary purpose of sprue in casting mold is to feed the casting at rate consistent with the rate of solidification. Is that it? Act as a reservoir for molten metal, the second one. And the third one is feed molten metal from the pouring basin to the casting. Pouring basin to the casting. Now this one is a pouring basin over here, okay? This portion over here is nothing but the pouring basin. Help feed the casting until all solidification takes place. So which one do you think is the primary purpose of sprue in here? This one is sprue, right here. So I'm going to just bind it. So yes, so what do you think about this? Come on. Which one? So what we are doing here is, we are just pouring in the molten metal through sprue, right? It's a passage here, isn't it? Without sprue, the pouring of molten metal is not possible here, right? So what do you think? So C. Prince says it's C, Logesh says it's C, Harshvardhan says it's a C, Venkat says it's a C, right? And Samar says it's C, and Jeet also says it's a C, right? There has to be, obviously it cannot be B, right? Act as a reservoir for molten metal, because riser does it, right? Riser acts as a reservoir for molten metal. Similarly, D also is riser, okay? So D I'm just taking out. Now we are just left with A and C, okay? Now it says the rate of solidification. So feed the casting, obviously it feeds the casting, but no, it doesn't do it with the rate of solidification, right? It just feeds the casting. That's why it's a C. Yes, Ranvin, you're right. It's a C, okay? Because it has nothing to do with directional solidification, isn't it? We have seen that. Yeah, Sanjeev. So how many of you got correctly? Just type in I if you got it correctly, okay? Yes, good, guys. I'm really happy to see you doing here, okay, performing here. It's really motivating, right? It's really an amazing show here, okay? Is that good? Is it good? That's what it is. Reservoir means that, acts as a reservoir for molten metal. Reservoir means that, it's always stored, a storage place out there, right? That's what it is. Yes, so let's talk about this. Hardness of green sand mold increases with. Now this is a tricky question, all right? Okay, so Ranvin says it's I, Venkata says it's I, TPM says it's I. Good, 3 people got it correctly. Good to see that, guys. Okay. Okay, Sri Kumar, Sanjeev, Harshvardhan. Good, good, good. So around 7 people out there got it correctly. Good. Good. Now let's talk about this. Okay, hardness of greens and mold increases with Okay, so hardness of greens and mold increases with increase in moisture content. Okay, so it should be just increase. Okay, it should be just increase in moisture content beyond 6%. Increase in permeability, decrease in permeability. Okay, so what is permeability? We talked about yesterday. Again, we are going to talk about it. So permeability means what? Ability to flow gases, right? Permeability means that ability to flow gases through it. All right, is it good? Now here, increase in moisture content beyond 6%, increase in both moisture content and permeability. Now, okay, let me tell you this. Okay, let me give you a hint. All right, now let's see this. Now, hardness for a fine grain is more than for a coarse grain. Now, can you please, now again, just understand this. Okay, so hardness of a fine grain is more than hardness of a coarse grain. Okay, is that good? Okay. Now here, okay, so fine grain. So let's talk about permeability. Okay, because we have seen that permeability. Okay, let's say that we have coarser sand. Okay, coarser means that it's bigger, something like this. Okay, so we have coarser sand like this, right? This is a coarser sand. And what is a finer sand? Finer sand are small, right? Something like this. So which one of these has more permeability? Finer sand or coarser sand? So ability to flow gases here, right? This is what we say. So what I'm asking is, okay, this is a coarser grain and these are the finer grain. Okay, so what do you think happens to permeability for coarser? All right, so coarser, which one is having more permeability? So coarser will have more permeability because it has more gaps here, right? So I'm going to write permeability of coarser is greater than finer, right? Is that good? Is that good? Yes. So permeability of coarser is greater than finer. Now what we have seen here is that fine grain is having more hardness, right? So fine grain hardness is more than coarse grain hardness, right? Yes, Banat Babu Ramu, you're right. Coarser sand, Prince, yes, you're right. So coarse grain, so fine grain hardness is more than coarse grain. So what is the meaning of that? Yes, exactly. So permeability is high. Yes, TPM, you're right. Okay. So what is the meaning of that? So what is the meaning of that? Coarse grain, obviously, coarse grain will have more permeability, right? Coarse grain will have more permeability, but which one is more harder here? Finer grain is more harder here, right? Isn't it? Yes. So hardness is, can you tell me the relationship of hardness and permeability here? So which one should it be? Decrease in permeability will will have increase in hardness, is it? And fine grain is harder. We have seen it here, right? So fine grain is harder here. So what do you think about this? So if fine grain is harder, so what we see is decrease in permeability will have increase in hardness here, right? So hardness is inversely proportional to permeability. Always remember this, guys, okay? So C should be the answer here. Yes, so how many of you got it correctly? How many of you got correctly? Just type in I if you got it correctly, okay? Yes, Prince, you're right. Hardness is inversely proportional to permeability, and I've proved it, okay? Why is it so? Yes, why is it so? Because decrease in permeability means it's finer, right? And that means that it's harder, that's why. Okay, so we are done. Yes, so let's get to another question. With a solidification factor of 0.97 into 10 to the power 6, the solidification time for a spherical casting of 200 millimeter diameter is. So yesterday we talked about it. Ranvin, if you told it first, good, congrats, okay? Yeah, good. So Sri Kumar, Sanjeev Kumar, Venkatesh, Harshvardhan, Manoj, Ramu, Ranvin, right? Sanjeev. Mechanical also says it's a high. Okay, fine, good. Pradeep, yes, good. So what is given to us? So solidification time is given something like this, right? TV upon a whole square, right? So K V upon a whole square, isn't it? Yes. Now K is already given to you like this. So 0.97 into 10 to the power 6 seconds per meter square. It's given to you, right? Now diameter of the spherical casting is also given to you. That's nothing but 200 mm. So that's 0.2 mm. So radius here is how much? 0.1 mm, right? Isn't it? Yes. So V upon A is how much? So what is the volume of sphere? Volume of sphere is 4 upon 3 pi r cube. And what is the surface area? That is 4 pi r square, right? So this is nothing but what? So r upon 3. Okay, so V upon A. Are you getting it? D? Okay, let's see. So V upon A equal to R upon 3. So V upon A whole square equals to R square upon 9, right? Okay, so TPM says it's 10. Is it B or D? So there's a clash, okay? So V upon A whole square is R square upon 9. So what it means is, so T equals to K R square upon 9, right? Am I correct? V upon A is pi 4 upon 3 pi r cube. This is 4 pi r square. So V upon A is r upon 3, right? R square upon 9. So K is given to us something like this. So 0.97 into 10 to the power 6 into r square upon 9. So r square is what? So yeah, so this should be in meters, right? Sorry, this should be in meters here. And r square is 0.1 whole square. Okay, so how much is this? Are you getting it? So how much are you getting this? Is it C? People are saying C. So there's B, C and D. Yes, so how much are you getting that? Is it C? 97 and 6 square. I'm getting it weird. 9700. Okay, so this is r k into r square upon, we also have a 9 here, right? So how much is this? So upon 9, so 1077, right? So we are getting it as 1077.77. So this is seconds, right? So I'm also getting it as B, okay? Is it good? So it's B actually. ठीक है? Hello? Kiran Kumar, B. Yes, B is the option here, right? ठीक है? Is it good? Now, how many of you got it correctly? Just type in I. I want to see all the champions out there, okay? So, how many? Jeet, I'm not getting it as C, right? So, B is the option here, isn't it? Yep, so the next question. Yes, Ranvin, you're right. Yes, you're right. TPM, Kiran Kumar, TPM. How many of you got it correctly? Okay, now please tell. Okay, let's see this question. Okay, misrun. So misrun is a casting defect which occurs due to. Let me tell you. Okay, fine. Now this is a misrun. Okay. Now let's say that this is cavity. Okay, this is cavity where the molten metal flows. Okay. And this is sprue. Okay, so lots many people, Pradeep, Ranvin, Sanjeev, and TPM also got it correctly. Abhinash also got it correctly, right? Prince, Logesh, yes, good. Ranvin, okay, good guys, okay, good, you're doing good. Okay, so what is happening here is, this is misrun. Okay, so somehow the molten metal is not able to completely fill the cavity as you are seeing here, right? So the molten metal is not able to fill the cavity here. So why it should happen? You have to think like that. Isn't it? So which one of these is the most accurate explanation of why this should not be happening, right? Okay, Kiran Kumar says I very late. Now please tell me, okay, why this should happen, that the molten metal is not able to flow to the cavity. So this is misrun here. Are you getting this, guys? So which of the option, right? So very high pouring temperature of the metal, insufficient fluidity, absorption of gases, or improper alignment of the mold flask. So what do you think? So it should be what? It should be B, right? Fluidity is not sufficient. That's why it's not able to fill it, right? So that's what it is. Yes, so fluidity. Yes, guys. So most of you got it correctly. Congrats, congrats, congrats. Okay, now the next question. Gray cast iron blocks, okay, these are given to you, okay, gray cast iron blocks are to be cast in sand molds, okay. Yes, Sanjeevi, B is correct. Kiran, yes, B is absolutely correct, okay. Now shrinkage allowance for pattern making is 1%. Okay, it's given to you. Now the dimension of gray cast iron blocks are given to you something like this. So 200 into 100 into 10. Okay, this is millimeter cube. All right, this should be millimeter cube. So these are the dimensions. Now shrinkage allowance for pattern making is 1%. Yeah, Abhinash, you're right. Sri Babu, you're also right. Atul, Pradeep, yes. So what is given to us is these dimensions are given to us. Okay, so 200 into 100 into 100, sorry, into 10 millimeter cube. Okay, now shrinkage allowance for pattern making is 1%. So which shrinkage is it given? Now pattern, is it going to be bigger or lesser? Now pattern, is it going to be greater than casting or is it going to be lesser than casting, right? How B is correct, Ankit? If it doesn't have fluidity, then only it might happen, right? Because of lack of fluidity. That's what we are saying. If it has fluidity, it will fill the entire portion, right? ठीक है? Okay, chalo. Let's do this. So the ratio of volume of pattern to that of the casting will be what? Is it 1.0? Now please tell me, okay, is it volumetric allowance or is it, a linear or a dimensional allowance? That's going to be bigger, right? Satish, a very big hi to you. So this is correct, right? So pattern is always made bigger than casting because of solidification, right? Because of contraction, isn't it? So it's always greater than casting. So obviously, so ratio of volume of pattern to that of the casting is not, it cannot be 0.97 and it cannot be 0.99. It can be either 1.01 or 1.03, right? Isn't it? Yes. Now, so what it says is shrinkage allowance for pattern making is 1%, right? So the ratio of volume of pattern. So what is given is shrinkage allowance per side is given, right? It's per side, that is nothing but 0.01. It's not volumetric actually, okay? It's per side, so that's what it is. So I'm going to just write 1% here. Okay, so shrinkage allowance per volume should be how much? That should be 0.01. So this is nothing but 0.01 into 0.01 into 0.01, right? Because this is per side that is given to us. That is 1%. Alright, so how much are we getting that? So how much are we going to get that? So this is 0.01. 1.03, 1.03. So people are saying 1.03, right? 0.01, 0.01, 0.2.06. Okay, so let's take it otherwise, okay? Let's just take it otherwise because, okay, fine. So shrinkage allowance per side is 0.01, we are saying, all right? Okay, so volume of pattern. Okay, now per volume is going to be how much? It's going to be D. Okay, Lokesh. Okay, those who are saying C 1.01, why they are saying C, okay, and those who are saying D 1.03, then why are you saying that it's going to be 1.03? Just comment. Just comment, guys, all right? So if you are saying it's 1.01, so why is that? Yes, TPM, you're right, okay? Yes, you're right. Exactly. Yes, you're right. Yes, you're right. Exactly. Are you getting this? Hello. So what we are going to say here is that, so the change here, so the change here is going to be, so is just getting changed by 1%. So the percentage change here is going to be 1.01 into 1.01 into 1.01, all right, because it's nothing but it's per side, okay? So change per volume is going to be this, right? So 1.01 into 1.01 into 1.01, so that's what you can you can calculate it, okay? Are you getting this? So shrinkage allowance per side is this one, so change per volume is going to be this one, right? So 1.01 into 1.01 into 1.01. So how much are you getting this? Are you getting it 1.01 or are you getting it 1.03? Yes, exactly. So yes, TPM, you're right, exactly. So D, you're getting a D, right? So 1.01. So this is nothing but 1.03, okay? Are you getting this? So yes, it has to be D here, all right? Is it good? Hello, is it good? So D is the option here. Now let's do this, okay? A mold has down sprue whose length is, okay, so sprue's height is given to be 20 centimeter here, and the cross sectional area at the base of the down sprue is 1. So that's nothing but 1 centimeter square. The down sprue feeds a horizontal runner leading into the mold cavity of volume. So volume is given to us something like this. So that's 1000 centimeter cube, okay? The time required to fill the mold cavity, okay? It's a okay, horizontal runner. It's a horizontal runner to fill the mold cavity, okay? Okay, fine. So the time required to fill the mold cavity is given by volume upon area into velocity. Okay, this is the time required. Now velocity here is nothing but under root twice g of h, right? Is that good? So what we have here is, okay, now height is given in centimeters, so you can also take g in centimeters, okay? So height is in this into 20, so how much are you getting that? Now Satish, because this is a startup series, right, so no new questions, all right? We are just trying to build the base according to the questions that appear in competitive examinations, okay? We are just going backwards. Questions are leading to understanding. Chalo. So this is the velocity that you need to calculate, okay? Now, so the time here is, volume is given to you something like this. So 1000 centimeter cube, okay, upon area is given to you 1 into velocity. How much are you getting this velocity? 2 into 981 into 20. So how much is it? So root of answer is 198.09. Right, so 198.09. This is centimeter per second, right? So 198.09. So how much are we getting this? 1000 upon 198.09. So that's 5.04, right? Exactly, guys. Good. So 5.04 seconds. Is that good? Yep. So B is the correct option here. Are you guys getting this? Hello? So this is the formula of time taken to fill a mole cavity, okay? Is it good? Is it good? Yes, TPM, I agree to it, right? So that's why, we are talking about building basics here through some questions that have already appeared here, right? So if you can do it correctly, obviously every one of you can do it correctly, right? So the question here is that can you also repeat it there? Okay, can you also replicate this confidence in the actual examination, right? Every one of you can solve these questions, right? Given that you know the formula, isn't it? Okay, fine. So the next question. Which of the following engineering material is the most suitable candidate for hot chamber die casting? Okay, now this shows a diagram or an image of hot die casting chamber, right? So what happens is the molten metal is, this one is a molten metal, okay? Now through this plunger rod, this plunger is moved in this direction, okay? Now this hot molten metal is poured into a mold cavity like this, okay, and there the solidification takes place. So similar. All right, now this is how we do a hot chamber die casting here. Yes, TPM, obviously. So yes, top gating, you're right. It was never mentioned, right? Bottom gating, top gating, right? So that's why it is. Now what happens is that this gooseneck, this should not melt, okay? This one is nothing but this gooseneck passage, it says, right? So this component over here, it should not melt, okay? Otherwise it's going to fail, isn't it? It should not melt. So hot chamber die casting will only be used for what? It will be used for low melting point alloys. Low melting point alloys, because we don't want gooseneck to melt, okay? So it should not melt. That's why we are saying that, okay, low melting point. Yes, exactly, Abhinash, Ranvind. Yes, so it is tin, all right? Tin is low melting point alloy. Is it good? Is it clear? So this should not melt. So gooseneck should not melt. So let me write it correctly. Gooseneck should not melt. So hence the low melting point alloys can only be done in hot chamber die casting. All right. I think this is clear to you. Is it good to you? Yep. So again, on the next classes, we are going to have a discussion about casting defects. Okay. Yeah, Ranvin, you are right, okay? Yes, you're true. It's very true, okay? So the casting defects, we'll talk about casting defects, and today we just talk about misrun, okay? So we already talked about misrun, and tomorrow we are going to explore more into this topic, all right, guys? Now, yes, now we have a green card for GATE, NLC and other exams, okay? And okay, so 12 plus 4 extra months excess, so 4 extra months excess that we are giving to you. Okay, now we have a sale from 4 p.m. to 10 p.m. All right, you can tune it for it. Now we have the achievements that we have. You can obviously appreciate it here. And my name is Rahul KANYAL, and I'm going to see you again tomorrow at 2 p.m. on concepts on fingertips. All right. And mind you that we are doing questions first, and we are trying to understand or derive our understanding through questions. Okay, so that's what we are doing. We can also do the reverse thing. Okay, first understand, then do questions. This is also a possibility. Okay, yes, Satish, you're right. So that's what it is. Yes, you're right. Okay, yep. So I'm going to see you again tomorrow at 2 p.m. that is concept on fingertips. And please share this video. If you have not subscribed to our channel, you can go there and subscribe it, and also share the news that such classes are going on, guys. All right, because if you help others, okay, the whole universe will come and help you. All right, and be blessed by the divine. Be blessed, all of you. And just keep on smiling, keep on being satisfied, and keep on being safe. All right now you need to be safe. We all need to be safe, otherwise this doesn't make sense, right? Isn't it? Yes. So I'm going to see you again tomorrow at the same time. All right, so Ranvin, let us do one more question. Is it? So one more question. This is the one more question if you want to see. Okay, this is again from the previous gate. If you can do this, Ranvin. Okay, fine. So please do this. All right. If you want. So Ranvin say that let's do one more question. Please do it. Then just tell me which is the answer. Time equals to K V upon A whole square. Okay. Now it says that, okay, volume of a cube and volume of sphere are equal. So volumes are equal here. So T is nothing but inversely proportional to A square, right? So can you please tell me which answer should you have? Now please tell me. Okay, you have 2 minutes here. Are you guys listening to me? Hello? Swapna, okay, fine. So Swapna, you can come back tomorrow, all right? So please come back tomorrow, and then then we'll see it. Okay. Okay, one more question. D. Ranvin says it's a D, right? So can you please just go back home? Yes. So yes, you have Satish also says it's a D. Then this is a formula here. Okay, T is inversely proportional to A square. All right. So time taken by cube to time taken by sphere is what? Area of sphere upon area of cube whole square, right? Yes, so area of sphere, how much is area of sphere? That is 4 pi r square. What is area of cube? We are talking, not cross, we are talking total surface area here, right? So that is nothing but 6L square, isn't it? Yes, so please find this. So 4 pi upon 6 whole square r upon L to the power 4, hence it's going to be D, right? Ranvin, you are happy? We did one more question just for you. So D is the option here. Just take care of this relationship that we have talked about. So K V upon A whole square, right? So that's what it is. Is that good? Yes. So I'm going to see you again tomorrow, guys. All right. Until then, take care of yourself. Keep on washing your hands. Keep on smiling. And don't give up. All right. We are done. Okay. Bye-bye. Take care.